Hello, this is Carl from lunchboxsessions.com. Hope you're doing well today. Thanks if you've been with us through the whole series, and welcome if you're brand new. This is number 7 in our series so far this year. The 8th one is coming up before too long. That'll be on August 25th on Load Sense Systems. So please do come on back for that one. Today's topic is slip-in logic cartridge valves. And lots of interesting things to share with you in the very short amount of time that we'll have today. I've got some slip-in logic cartridges right here, and some little pieces that we can just look at for a minute before we get into some of the more introductory things. And let's have a look. So I just took one out of a container here, a Rexroth LC16 A10 E7. What do all these letters and numbers mean, right? Well, in short, an A series cartridge will be a 2-to-1, which means that there's twice as much surface area here on the bottom where the A port is, as opposed to the annulus surface area that comes in through these holes on the side of the bushing or sleeve. And then there's going to be a very important surface area that we're going to be talking about called the pilot surface area here up at the top, and there's a spring in there. On the smaller series of cartridges, the 16s, the 25s, the 32s, there's often a cover. And that's not there on the larger ones, okay? So that's just a little something there from one of the cartridges. I better keep them all in their canister to easily get myself confused. Here's another one, just a quick look at. We'll take the cover off of that one, and we'll see that this one too, oh, there's something extra on the bottom. This one has a damping nose. Dampening nose helps us be a little bit more gentle with the flow and the pressure bang as the valve opens up. That nose sticks much further down into the bottom port, the base port. We'll be talking about the base port. We'll be talking about an annulus port as we get into the manifolds where the flow comes and goes from. These springs can be anywhere from what, about a half a bar, 7.5 to maybe 4 bar, like 60 psi, roughly. Yeah, that's it. There we go. Oh, here's one more. This one's a little different. Again, pull that cartridge out, and we'll find out that there's absolutely no annular surface area. It's the same on both sides. We might call this a balanced. Some people would call it a 1-to-1, comparing the base to the pilot surface. Some people would call it a 1-to-0 because there is no annular. Yeah, there's lots of little terminology things for us to get into here today as we study. And these balanced style that don't have that annulus surface area are so often used for work with a cover that has a pressure controller. We're making a pilot-operated relief valve out of this. But hey, in a minute I'm going to have to show you some context and see how these are actually used on different machines. Here's one from Moog. Moog makes their cartridges maybe a little different in that the seat has a more of a sharp squared edge on the inside, and the tapering that hits somewhere in the middle of the taper. So not as easy to calculate by putting your caliper on the poppet what your surface areas are, because you really do also have to get inside the sleeve on this model to finish figuring that out if you lost track and didn't have your data. And yeah, Mark and I are always struggling to figure out the data. Mark's with me here in the shop today, everyone. Mark is here. Mark Many Letters. You saw him on the previous episodes, and so he's going to give me a hand. We've got so many things to work out today. So happy to have Mark's assistance with me here today.
Happy to see this side of the production.
Yeah, we don't have a boom Mark on Mike, so you probably can't hear him quite as well right now. But yeah, Mark's happy to be on this side of the camera and lend a hand, so that'll be great. Yeah, let's just chat a little bit more about some introductory things here. Don't forget to log into your YouTube account or your other Google services if you're going to use the live chat and send us your questions. We'd love to have you interact with us. Send us your questions about slip-in logic cartridge valves and put those on the chat. If you've got other questions for us, for me or Mark, the things we do with our company, our services and what have you, or other hydraulic topics not related to slip-in logic cartridges, then please email us. info@lunchboxsessions.com is great. or look for me on LinkedIn. I'm on there quite a bit. Look up Carl Dyke, industrial teacher. I'll be glad to make a connection with you if you invite, and then we can continue to chat that way. Mark Many Letters if you're looking for him on LinkedIn, and feel free to engage us in a chat, and we'll be glad to answer your questions. Before we get too far, a bit of a shout out to my good friends and our partner at fluidpowerworld.com. Fluid Power World is your great resource for hydraulic components, for pneumatic components. There's quite a bit on system design and system engineering, lots of great knowledge to be had in that regard. And this year, the Fluid Power Technology Conference is online, as are so many conferences. And if you head over to fluidpowerworld.com and look on their top menu for the event link and pull down on the event link, you'll find that Fluid Power Technology Conference. The first event was already last week, a week ago today, 7 days back. Joe Kovac opened up with a great talk on innovation in hydraulics. Well, the next one is next week. They're 2 weeks apart. So the next one is next week, exactly a week from today. Check that one out on the menu. My good friend Josh Cosford from Higginson Equipment and a contributing editor at Fluid Power World. He'll be presenting on fluid power seals, and Josh has been in the hydraulics machine shop business and cylinder making business for a long time. So I know he's got a lot of useful tips to share with you next week on the Fluid Power Technology Conference, which is online. All right, before we get too far into the little technical bits and pieces, and I'm sure Mark will remind me to point out some things about the tiny little drill hole orifices that, oh, this one's plugged. This one's got a 30 thou, 0.030. I don't know if you can see in this hand here that I'm moving the very small 0.15, but these orifice plugs are also threaded into either the manifold body, or sometimes they're here in the cover. And wow, from a maintenance point of view, don't let that oil get full of particles. Things will get interesting fast. Pulling these logic cartridges out can get interesting. So this is a tool from Rexroth for removing a Rexroth logic cartridge. This particular tool can get underneath the cap. Once the cap is out, it can get right, you got to be careful not to scratch the inside. It can get right down inside and pull that out. So that's an official tool. If you haven't seen that one, not everybody has. For pulling out our Moog cartridges, we have this big fancy monster here, sort of an inside internal puller. Probably looks like something you might use to pull a bushing or internal bearing out of a pocket, and perhaps it's very similar to exactly that kind of puller. All right, let's have a look at some photographs. Mark and I often like to start there and have you look at with us at some of the Slipin logic cartridge machinery installations we've bumped into in our years of travel. Here's a couple of very unassuming looking caps, covers. They're called covers over the top of a couple of Slipin logic cartridges, and I believe in this case these two are just being used as basic check valves or basic relief valves. You can't even see where the pilot passage is. It's somewhere else inside that manifold block underneath, and very unassuming looking. You just see these square covers, 4 bolts, doesn't look like anything interesting, but that very live activity of these poppets is down there. I mean, I guess to some degree what I've been showing you, these poppets, it is a very simple looking device. It looks like a close relative of a simple check valve, and yet we're going to find out that the Slipin logic cartridges are doing quite a bit more than just acting as a check valve, but they certainly can do that job, and they certainly are commonly found doing that job. Here's a much larger manifold block full of valves from a oriented strand board press. If you know OSB, oriented strand board, a type of composite panel for construction for sheathing on the outside of houses and buildings. And so again, might be a fairly basic function under the covers that you see on that manifold block. Here's a manifold block from a piece of mobile oil field service equipment. And this particular block was a part of control of flow to a hydraulic motor turning a fan, a very large cooling fan. And so you can see the covers on the left side, on the right side. You can even see that cover down below that has that pressure adjustment pilot. And so what we'll probably find out here as we bump along is that sure enough, there is the poppet on the left side of your screen. If you're looking, there is that poppet that was in that bottom cover. No annular surface. That balanced poppet, same surface area top to bottom, no B-port annulus surface area, and that's often being used. DB, this is a Rexroth model, DB, is being used in a pressure control, a relief valve, or a sequence valve type of application. Whereas the other two that were on the side on that manifold, these are those 2-to-1 surface area cartridges that are also very popular. Flow in both directions is possible, but in this particular case, the schematic had oil flowing in only one direction because you typically spin the fan in one direction. Yeah, you don't often show the symbols. These are the ISO symbols. You don't often show the symbol drawn in a kind of an upside down fashion. This one down here in the lower center, if you're following on screen. But it's drawn upside down, because I think in this case that's a good interpretation of how the manifold block was laid out, and probably makes sense for troubleshooting to see it that way. Yeah. And by the way, while we're talking about troubleshooting, such a simple device, what really goes wrong inside? Other than O-rings perhaps becoming damaged and leaky, there isn't much else. If the poppet is stuck partly open, or stuck wide open, or stuck shut, these are questions that often get answered by starting to address more rigorously your contamination prevention program. Otherwise, these components that we're going to be looking at today are very simple in nature. Here's out of a shovel. I believe this is out of a ONK RH400 shovel, maybe more commonly thought of now in newer models as a Caterpillar 6090 shovel. But on these swing motors for swinging the upper works, on a block that is mounted at the top of these bent axis motors are slip-in cartridges right there at the hydraulic motors for swing. And in this case, it was a part of a circuit. There you see them in a still shot from one of our live schematic simulations, but you see those cartridge valve symbols there being used to create sort of a check valve scenario or a porting scenario that lets the shovel still have swing, even if one of its two prime movers, the giant diesel engines, if one of those two dies, it could switch over to single engine mode, and perhaps the shovel can't swing quite as aggressively or quite as fast, lose some strength, but at least it's still there functioning. So that's it. Slip in cartridge valves right on top of the motor ports for swinging a shovel. Let's go back inside an industrial plant. Again, this is back in a panel board plant, an OSB plant, I believe. That's where these came from. Yes. And now you see something different. You see a Poppet Travel limiting screw. This one is very basic. You just get your hex wrench inside and you lock the jam nut on the outside, and there's a threaded rod inside that lets you limit the travel of the poppet as though you might be limiting the flow and setting the speed of a certain circuit. And if you remember a moment ago, I showed you a poppet out of one of these that had a damping nose on it, this extra little piece here. After the seat, there's an extra piece, and we'll get into that a little bit more. The damping nose, that's often being used then together with this type of scenario. So you see that both on the left and the right-hand side there in blue. One's able to adjust more readily by hand. The other one requires a bit of a wrench scenario to get it adjusted. Okay, we'll show you a scenario like that here on our panel too. Here's a bit of a zoom out view from another manifold block in that same plant. Pressure control, but with a security cap over the top to discourage interference with the setting. Doesn't always work, does it? Basic cap, well, you see a number of different things. And of course, part of the big convenience to simplify hydraulic systems is to mount other valves that are involved with control to that same manifold. How many hydraulic hoses disappeared, which is leakage? How many hoses disappeared, which is also friction and therefore pressure drop? So a lot of efficiency to be gained and a lot of simplicity to the maintenance of a hydraulic system overall, to engage in the use of manifold blocks with slip-ins and other types of control features that might be located nearby. Yeah, here's a schematic from that exact manifold. Starts to get a little bit of a tangle. Lots of things to learn, even in just this small amount of componentry that we're looking at here. Won't have time to decode a circuit such as this one just now, but there is pressure control there. There's basic directional, basic flow control and check valving going on there as well. Yeah, from another plant application, there you go. You can see that stroke limiting rod meant to be adjusted by hex key and jam nut with a wrench on the outside to set the flow rate through one of these cartridges and lock it in place, and then we're off to the races. Wow, there's a whole series of banks. I think it was one for each pump supplying in this plant, and there's what you see on each one of those. If you're looking at the top of these symbols, I'll just be over here on the right. A little hard to see my mouse icon in this particular photo viewer, but I'm over on the right. It says NG25 below the designation of the component, so that lets us know it's the 25 millimeter size. We'll have to talk about what that means, but that's the second smallest. And whereas over here in the middle, look over here in the middle at the lower notes as the P-port, the pump supply is coming in, NG50. Well, so there's between the 25, there is a 32 and a 40, so 50. There was also 16, so that's the fifth largest coming up from the bottom in terms of sizes available in slip-in cartridge cavities. And on the cover, you see that diagonal arrow passing through the double lines, letting us know that there's a mechanical adjustment there, can be adjusted. That's that stroke limiter rod. Yeah, lots of details. Oh, back to mobile equipment again, right? Caterpillar 385, 390, some of those really large excavators that some people almost call a mini shovel, pretty large diggers. And there's a slip-in cartridge being used as a part of the boom lock circuit, if memory serves. That symbol doesn't show up in an awful lot of mobile machinery, but it does so with increasing frequency as the days go by. So last two little slides here are images to think about. You'll hear about ISO 7368, 2016 being the more recent year, previously 1989 before that. And that ISO number for slip-in cartridges has more to do with the machining of the cavities. It's not so much about how the manufacturers choose to make the valves. I mean, they have to conform to the cavity, of course, but they have more freedom there. No, following the ISO 7368 is about milling the cavities that the valves drop into. And so when you hear about the smallest size, which is what we are going to be working with here, we have to work with the smallest size because we're only working with 1.5 gallon maximum flow, and we move our equipment around. We don't want to break the axles in our truck and trailer, so we keep things light and work with the smallest. Well, that NG16, that smallest size, is 16 millimeters, and that's to be picked up where you see the big letter A on that bottom base port, and then go down just below that to the diameter symbol D2. The diameter of that passage entering in from the base, that is your 16 millimeter passage. Yeah, so if you were looking at this whole cartridge saying, yeah, that's a lot bigger than 16 millimeters, all that, yes, it absolutely is. The diameters are larger where that whole cartridge assembly slips into the cavity. But diameter 2 is that flow passage coming in from the base. And this image that you're looking at here shows up commonly in the technical information, the data catalog for slip-in cavities from the various manufacturers who make them. This is basically an image that comes over from the ISO standard. Currently in common play, there are 8 sizes from 16 millimeters up to 14 up to 100 millimeters. I think there have been 2 more larger sizes along the way, but they're not as common. It's already a very large valve by the time you're up at NG 100 millimeter, or 4 inches roughly, and that's a very large opening down there on the A port. The actual valve itself turns out to be much, much larger. This is an NG 40 sized valve, so you can see what we're talking about. The valve itself gets very large. Huge flow rates. And that is one of the key advantages of these valves, which we'll get into here in a little more detail as we move ahead. Let's jump to a simulation just for a moment to bring things to life a little bit more. Let's jump over to Lunchbox Sessions, and let's head over to the cartridge valve session. We've got all kinds of fun things here. Let's see. Let's open up a simulation of a generic cartridge valve operated system with just one cylinder. I'm just going to hit the pause button and just tell you a little bit about it here. You can see the symbols there for 3 cartridge valves from left to right, CV1 to CV4. And on top of each one, and this is fairly common, I don't know if you can see this with the camera or not, but over here, we've got a directional valve mounted on top of a cover, and the cover over top of a manifold, and down inside there somewhere is a cartridge valve. We've got a solenoid operated valve mounted right on top. And that's very common for deciding the moment of when you're going to put pilot pressure in on top of that cartridge, or when you're going to bleed it off to tank. And so that's what you're seeing in this schematic, is you're seeing 4 solenoid operated directional valves. Currently 2 of them are energized, SV2 and SV4. And when I hit the pause button, which I've hit, it basically just gives us a cylinder of infinite length so that we can stop and study the flow path for a prolonged period of time and understand what happened. So by energizing SV2, what you'll see we've done here is we've taken pilot pressure from the pump, and we've let me just start again here. I'll start at the top of CV2. At the top of CV2, which is blue, which is our drain pressure, follow that out and notice that we've taken the CV2 pilot area on top of that cartridge. That's the largest surface area on top of the cartridge, and we've taken that surface area and we've connected it to tank, drain pressure. So it's very easy to understand why the pump will have come up from the bottom, pushed on the base part of that cartridge, pop it, pushed it open, flow out the side annulus B port and into the base of the cylinder to extend it, where oil coming back from the rod end of the cylinder as the cylinder extends is exiting from B to A flow. That's sometimes called annulus flow, whereas what was happening over by the pump was called base flow. This is annulus flow going from B to A and back to tank. Well, pressure oil coming from that rod end of the cylinder does in fact push up on the surface area if it's been provided, and the symbol indicates that there is surface area there, has pushed up on that poppet, and that poppet can move up. Why? Because it too has its pilot area on top of the cartridge vented to tank pressure. So very easy to move the poppet upward and have that cartridge valve open. So that's a pretty easy one to understand. Let me continue here. We'll turn off our pause. We'll hit the end of stroke, and then our controller will change the action of the solenoids in our plant. And now we're into retract. And so look what's happened. Something very similar. CV1 and CV3 have been vented. They're pilot ports at the top of the cartridge, which is the largest single surface area, more on that in a minute, has been connected to tank. Whereas CV2 and CV4, those cartridges are being held shut by pressure from the pump, which travels through solenoid valve 2 and onto the top of surface area, pilot surface area on top of CV2. Same thing happening over here on CV4. We're using the pump as a pilot pressure on the largest surface area available. That's the pilot surface area at the top to hold CV2 and CV4 closed. And that's giving us the ability to make these cartridges create a retract. Now, what's interesting what's happening there. Let's freeze that one. Did you see how fast that cylinder was extending? That was cylinder regeneration extend. And if you know what regeneration flow is in regenerative extend of a hydraulic cylinder is all about, it's all about taking oil flow coming from the rod end and regenerating it or combining it with new flow coming in from the pump over here where it says from pump, and you're being joined by other oil regenerated back from the rod end of the cylinder. And so now you have a really high, unusually high flow rate entering into the base end of that cylinder to extend it fast. And how's that being done here? Oh, that's being done by energizing only one solenoid valve. Well, this is going to get a little peculiar. So by energizing SV2, it's pretty easy to understand why that poppet went up. It went up because the pilot surface area is connected to tank, low pressure zone, and the pump came in and pushed on the bottom base surface in that cartridge and popped it open. So very easy to understand why flow happened there, but maybe the rest isn't quite as easy to understand. So let's look at the oil coming back from the rod end. The oil coming back from the rod end hits a T-fitting here and can go to the annulus CV4, which right now won't open. Why won't CV4 open? Easy enough to understand. We're taking pilot pressure from the pump and putting that on top of the pilot port, the largest surface area in the poppet, plus a little bit of booster force from the spring. I forgot to mention that so far, a little bit of extra force from the spring. And that's pushing it closed because pressure coming back from the rod end of the cylinder can only act on the annular surface on the B port. A port, which also has surface area, is being held at tank. No, there's not enough force being generated from the B-port annulus to pop CV4 open, so it stays closed. Now, you might ask yourself, then why did cartridge valve 3 open? That is a little trickier, especially since you'll notice that SV3 is not energized, that the pilot surface area on top of cartridge valve 3 is not vented to tank. It is still pressurized by the pressure of the pump. What's happening here? Well, that's the largest surface area, and one would think that would keep the poppet closed. Well, okay, oil leaving from the rod end of the cylinder is being pushed out on a reduced surface area by a single rod cylinder. There's a little bit of pressure intensification happening there. A topic we won't have time to study in any depth today, but due to surface area changes from the blind side to the rod side, pressure intensification happening, we've got a higher pressure coming in to act on the annulus B surface. We've got pump pressure to act on the A surface at the base. And so those two forces together are actually a little bit greater than what's happening from the pressure and surface area, and therefore the force from the top of the poppet. And this valve is likely not wide open. It's open enough to pass the fluid through there, but we're still under pressure on the rod side, pushing that through, and there we go. And it's important because if this top of this cartridge valve was connected to tank, then there would be some extreme poppet bangs and pressure changeovers when the PLC changes the sequences of our cylinder action. So this helps to prevent some extreme pressure changes and valve bangs when the sequence for our cylinder changes. That's a little bit advanced for the moment, but let's keep going. And so here we are again in retract. We saw that one earlier, and I think we have one mode here at the bottom to look at, and then we better move on. So we'll just wait till we get to the bottom here where it says unload, and let's see what state we're in. We're kind of in an idle state by energizing SV1 and SV2. We've just taken that pump flow and sent it right back to tank by wrapping around from cartridge valve 2 to cartridge valve 1. Yeah, we're in a situation where no flow is being directed to and from the hydraulic cylinder. The pump is just being unloaded right back into the tank. Lots of versatile things that can be done with 4 cartridge valves, a little bit more than what could be done with just a simple 4-port 3-position directional valve. All right, let's have a look at, one more application. Let's go to the pulp and paper business for a minute. And Mark and I like to help out with truck dumpers that we see out there where they tip the truck up at such an extreme angle to get the chips out the back for a pulp mill. And here is one of those truck dumpers that we bump into, and it has telescopic cylinders, as you can see here. We'll start the raising. You can see those telescopes going up. Here, second section. Here, we'll pause that. You can see where the pumps are at the bottom coming in. And here we have a couple of poppets, a couple of cartridge valves just being used as simple check valves. Here we've got the piloting on the B side. It's just connected up to the B side. Well, there's a bit of a pressure drop between A and B, so the pressure that will be left there won't be enough to jam the valve closed against the pump's pressure and flow coming in. So flow carries on, but if something happens, if a hose were to burst between the pump and the manifold, if the pumps were to die off, whatever the case might be, the pilot pressure will come back, act on the surface area, the pilot surface area at the top, and jam those poppets closed, giving them a check-like function once there is no pressure coming from the pump pushing its flow anymore. So they're just acting as basic check valves. Same thing with C3 here, just a very basic check valve. And then if I turn the pause off and wait until those cylinders at the top deadhead, yep, we're deadheaded. Let's go back down and have a look. Now that we're deadheaded, we're using a balanced type of poppet that has no annular surface area, R1 and R2, but has a bleed orifice through the middle, right? A balance orifice through the middle. Sometimes it's around the side here. These are now acting as relief valves based on the pilot section you see here, 1750 psi pilot section. That's just a small flow, as you know, through the orifices, but that has caused the pressure above the poppet to drop down far enough to make it easy to drive that poppet to the top and create a relief valve function out of those very same poppets. So this is a large truck dumper where you can use cartridge valves for both directional flow, relief, all those functions. Let's go into the lower mode and bring the truck dumper back down. Very easy now to control R3 and R4 and just direct flow directly back to tank right near the entry point to the manifold where oil is returning from the cylinders. Some orifices, some permanently fixed orifices there to help control the rate of the drop of those large telescopic cylinders. So there's a couple of applications for you. All right, a couple of things we should just cover in the slip-in cartridge lesson, and then we're going to move over to the hydraulic training panel after that and do some live demonstrations. So in our lesson, what is a cartridge valve? There's some pieces. We've kind of gone into that a little bit. There's the spring in the middle. Here's a cutaway. There's the poppet. There's the sleeve, or some manufacturers call that the bushing. And there's always going to be some kind of a cover plate. There's lots of variety there. Here, let's put a cartridge together and have a look. So there's the pieces going together like I've shown you earlier already. And then down into the manifold or the cavity, and the cover comes on. And there's an X and a Y pilot passage in most manifold cavities right close by. One's connected to the B port, one's connected to the A port, and in this case we've got plugs in there. We're not doing any special piloting using those particular passages, but sometimes there's orifices in there and connections up into the activity of the cover, as you are going to see. So why use these valves exactly? Just to recap on that, they're certainly very simple. So a standalone, one of these simple cartridges all by themselves is not that expensive as a single piece. Extremely durable, work very well with very high pressures because you're putting them into that large manifold. Work well with high flow rates because They don't cause much of a pressure drop like a spool valve does. It doesn't take long to get the oil in and out of the valve. There's not a lot of obstruction in there to make that 190-degree change of direction from the A port to the B port. So high flow rates happen well with minimal pressure drops and very little leakage because all these parts are somewhere inside that manifold. So very versatile. Lots of things you can do with them. Let's see here. Let's move down a little bit. Yeah, what can you do with the slip-in cartridge valves? They can and routinely are all of these things. Check valves, relief valves, flow controls, pressure-reducing valves, directional valves. All these things can be done with clever scenarios to control slip-in cartridge valves. I'll leave that puzzle for you to play with at some point if you log in. There we go, our slip-in cartridge valve symbol, spring, sleeve, poppet, the A port at the base. The B port comes in on where the annulus surface area is found. And here we have a number of scenarios for us to think through. A basic check valve where you have port A pressure closing in on the top of the cartridge valve in the pilot area, the largest surface area available. And so oil checking back against the A port, pressure coming and closing at the top, but this one won't be leak-free, this one on the left, because oil can travel down between the poppet and that sleeve, that bushing, and travel out the B port. A little bit of leakage can easily occur. And we're going to show you that in a minute on the training panel. On the other hand, the B port, oil that is being forced back against the cartridge in a check valve scenario might take that B port pressure again straight up into the pilot surface area on top of the cartridge and slam closed with that same pressure, the superior surface area that is represented up there. And now this one will be more tight sealing, very unlikely to see leakage because the same pilot pressure is going to push down on that cartridge, and we have a tight seal here where the poppet hits the seat. Very common to find an external source doing the piloting. You have lots of control options. And what you see on the right here is very common, where a shuttle valve may select the higher of two pressures from the A or the B port for check functions. And then if we turn the solenoid valve on and vent that pilot to tank, then the cartridge is free flow in both directions. Whereas with the solenoid off, it's a check valve for both directions. It will block for both directions. So lots of different scenarios. We can't cover them all. We won't have time. So here's a little bit of a study of the surface areas, and this is good for us to have a look at. In fact, let's have a look at the image on the right first. Area X at the top, sometimes referred to as Area P for the pilot. There's a few different designations and terminologies depending on whose manuals and literature you're reading. Don't get too confused. The largest surface area here at the top, and that'll be noted for our purposes as Area X. At the bottom here is usually a smaller surface area, but Area A, in this case, appears to be the same as Area X at the top. Well, this is one of those balanced cartridges. This is sometimes referred to as a 1 to 0 because there's no annulus comparing A to B. And some other manufacturers will compare the base, always the reference, to the pilot surface area at the top, in which case we're going to call it a 1 to 1. The unbalanced is what we see over on the left side of the screen here, where we've got largest surface area still at the top, for sure, Area A, Area X, the pilot surface, but then Area A at the bottom is one of our main surfaces for the control valve, but then there's an annulus surface. And I was showing you that earlier when I took a poppet out of the bushing and showed the camera. That annulus surface is your Area B. That's your annulus surface on port B. And that gives us an unbalanced poppet. And so what do we learn from all of that? Two types of flow, base flow, A to B, annulus flow, B to A. I think we mentioned that. And I think we already talked about leakage paths, so I'm going to skip over that one. The FPA triangle, force pressure area, this will be a busy aspect to your work if you're calculating what you might have in your cartridge valve poppet. What do we see in this brief animation here? Yes, we see pressure from from the pilot being vented out externally from the pilot cover, and B to A, that annulus flow is actually possible. It's possible for the pressure on the B port to work on whatever annulus surface is available if the pilot pressure above is gone, and open that cartridge and actually allow B to A flow, annulus flow. Seems a little less natural, I realize, than base flow. So there's surface areas, there's ratios out there. We won't have time to cover them all. We'll just look at some very simple things. There's that example of the balanced poppet, often being used for pressure controls, for building relief valves and what have you into the manifolds. The 1-to-1, if you're comparing base to the pilot surface at the top, or 1-to-0 if you're comparing base to annulus. But more commonly for the directional and flow control poppets, you're dealing with the types of poppets that have both a base surface area and the ring annulus available on port B. And so now there's a couple of different ways the manufacturers compare those surface areas. Again, they may compare in their catalog surface area A to surface area B. That's the example here at the bottom row where it says then it's a 1-to-1. But other catalogs may say, no, compare surface area A on the bottom to the pilot surface area X on the top. Well, in that case, that's going to make this one a 1-to-2. Yeah, the terminology gets a little confusing as you move from one manufacturer to the other. It's not always easy to figure out your interchangeability unless you do some calculating and look and see where the ratios are taken from. It is pretty common for manufacturers to have a 60-40 or a 66-33 type of surface area between base and annulus. But they almost all have one that has a very skinny annulus. That'll be somewhere between 4% and 10%. And the remaining 94 to 97% might be there at area A on the bottom. And that's what we're showing you here. And this type of poppet will generally only have flow going from A to B, very rarely from B back to A. And that's what you're seeing there. Very skinny ring annulus. The bottom area is about 90% compared to the 10% on the annulus port. All right, what do we see here? Here's a very common 2-to-1 from Rexroth, right? Where you have 2 times the surface area on the base that you have on the annulus. So let's just have a look and see what that might look like. 100% being referred to as being on the A port, then a ring annulus that has 50% of the surface area, and then 150% at the top, and they would call that a 2-to-1. Yeah, actually this is probably the better view here, a little bit more accurate in terms of the drawings, where the 2-to-1 does actually typically have this tapered surface. So let's go with this particular graphic here. So the bottom being the reference, and they refer to it as 100% the surface area. Well, we already know there's something larger. There is something larger already, and that is the pilot surface area at the top. But that pilot surface area adds up the ring annulus here of the top of the cartridge itself, the poppet, I mean, and whatever the first ring annulus might be as we drop down along the side, that would be a surface area at the top. And then down inside the bottom, where the spring bottom's out, that's also part of the pilot surface area that makes up this giant pizza pan yellow disc that you see at the top, being referred to as 150%. Whereas if we move over to the one on the right, 100% on the bottom, but only a very slim 7% on the ring annulus. So therefore, we'll speak of the top as 107%. Well, guess what? If you put your caliper around the outside of this poppet, and you put your caliper around the outside of the left poppet, they're going to be the same diameter. The ratio game is mostly about comparing what's happening on the base to that annulus, that ring surface area. That's what's happening there. So we're seeing a Rexroth 2-to-1, comparing area A to area B, the base to annulus, or we're seeing a Rexroth 14.3-to-1, which puts 7% on the annulus as compared to what is on the base. All right, that's probably enough for ratios, because after that we just have to spend time making measurements and doing some calculations with pi r squared. All right, calculating opening forces and closing forces. Well, if we were to take this example and say 1,000 psi coming in on our pilot, but acting on 2 square inches, plus also maybe a bit of a boost from the spring, but maybe also 1,000 psi coming in from the bottom for pressure, but only acting on 1 square inch. What state is the valve in? Is it open? Is it closed? And I think you know the answer there. We have much higher surface area on the top and a spring boost. So we know that this valve, as it stands at the moment, will be closed. Even though there's 1,000 psi pushing from the bottom, 1,000 psi pushing from the top against a much superior surface area keeps this poppet closed. No flow is happening from A to B. That valve's closed. Well, what else should we cover before we move on? We're just about done there. Oh, the damping nose, right. That damping nose, if it shows up correctly drafted on your symbols, we'll put a bit of a black coloration, a darkening in of the bottom surface area on the A, on the base, and that will let you know that there's that extra piece here. Look on the left side of the screen where I'm moving my mouse around, that little part of gray that dropped right down into the A port part of the sleeve, that's the damping nose, and that gives us the ability to have a little bit slower opening and closing times in terms of flow rate, to control the rate of flow as the valve opens. You've got a little bit of an option there. Although when closing, you may still encounter a bit of a bang because if flow is coming back from the B port, it's moving in the same direction as the cartridge. So sometimes not always easy to smooth that one out. But it does often give us the option to add this Cartridge Travel, the Poppet Travel limiting rod, this threaded rod, which may be down inside, and it just limits how far up that poppet can travel. And that's good if you're going to set a permanent flow rate passing through that cartridge for the speed of some part of operations in your plant. And in some cases, we'll even see a proportional valve mounted on top of the cover, no threaded rod, and then the pressure in the pilot area may be bled off very slowly. Again, with a cartridge that has the damping nose, and that might be used in a decompression circuit for a very large hydraulic press. There's so many different functions. We won't get into active control cartridges, which have an extra surface area that's beyond the scope of our time here today. So based on some of the things that you've seen there now, I should have mentioned earlier that there are some documents for you to find on lunchboxsessions.com/live there. You'll see that in accompaniment with this particular live broadcast, there's CDIG schematics there, the first file that you can open, and that will give you a bit of a picture of our plumbing. As Mark was reminding me yesterday, we've created a bit of a snake pit here, and it can be a little bit confusing for the eye to view what's happening with all of those many hoses. You don't have the benefit of the stereoscopic vision we have moving around here. You've got a flat view of it. So those schematics will help you sort of understand a little better what plumbing we're working with. And what we're going to do now is actually run the hydraulic system, is do some of these ratios for you and try to prove them. But maybe we should stop first, because I haven't done this yet, and tackle some of the questions you guys have. So let's see what you're asking today. Joel has asked, why do you have the reduced orifices on the pilot port? Yeah, right. Very good. The reduced surfaces on the pilot port are very handy for slowing down the rate at which that poppet opens and the rate at which it closes, to try to limit the amount of bang that can happen as that poppet comes off its seat and as it returns to the seat. Also takes out some of the minor pressure fluctuations that happens in hydraulic circuitry from changing that poppet position when maybe a small change is better to be ignored. So I hope that helps you a little bit there, Joel. Mubaris asked, how do we reduce pressure spikes when the logic valve opens and closes? Yes, very good question. You may need accumulators involved in your circuit. You may need as I was mentioning a minute ago, some cases a proportional valve is located on top of that cover and very, very carefully bleeds off the pressure from on top of that logic poppet, and then allows you to open as slowly as possibly. Hopefully slip in cartridges with a damping nose. I don't know if the camera could just be lifted up for a second to have a look over here. We'll try to find time at the end here to have a look at this particular valve. But this type of assembly is also very popular. It's not a separate slip-in cartridge and a separate cover. It's not. It's all one assembly that dropped into an NG25 sized cavity. So this belongs to the world of slip-in technology, but the cartridge itself is not separate from the cover. It's one assembled valve, and this valve is physically attached to the poppet below. It's not separated, and so it can give you very fine control of where that pop. This is a proportional throttling valve, 2 ports, and with proportional current coming from the amplifier card, we can actually very finely meter. Even though this thing is rated for 80 gallons per minute, that's a lot of flow. I've got the gain turned down so far on the proportional card that we'll be able to control the speed of this motor quite nicely with just 1.5 gallons per minute flowing through it. So that's kind of a crazy fun thing. I hope that helped a little bit. A question about the truck dumper animation, why the check valve stays open when the area at the top is greater than the bottom. Yeah, don't forget, Mubarak, that there's a pressure drop as flow passes through the cartridge. So flow from A to B passes through the cartridge. The pressure on the outlet side B port is not as great as it was coming in on the A port. And then don't forget that the surface area of the A port may be 2/3 of all of the surfaces on the bottom, meaning it may be 2/3 of what's available between the base and the annulus area, or it could be much more. It could be 90% or more. So there's quite a bit of force available there. Joel asks, how do slip-in cartridges differ from screw-in cartridges? Which style is more common? Yeah, that's right. You can get a lot of functionality that is common to slip-in cartridges out of very similar screw-in cartridges. And I think one of the advantages you get with a slip-in cartridge is that the cavity that the valve goes into is far less likely to ever be damaged because the cavity itself doesn't include any threads. So I think that's one aspect of it. There isn't any real possibility of torque bending moments in there where the cartridge isn't seated right. It goes into a perfectly cylindrical cavity, so it's not about watching how you torque the cartridge into place. The cover just goes on over top and you're good there. And so I think those are some of the advantages you get from that. Cavello says, could you advise what it takes to become a good hydraulic engineer? Oh, I'm not sure. I probably, like many professions out there in life, keep on studying. There seems to be an endless number of things to know in hydraulics, and the more experience one gets, the more you master your craft. All right, I'm going to carry on for now, and we'll come back to more questions you may have towards the end. Welcome everybody today. I didn't do this earlier. Welcome to all the countries. The list has grown quite long. We've got folks with us today from Finland and to Colombia. Wow, that crosses over some ocean right there. Chile right to the bottom of South America. Sweden back up into the north. Tunisia, United Kingdom, Romania, Kuwait, Saudi Arabia, South Korea, Panama, Turkey, India, Philippines, Russia, Iran, and Brazil. Wow, that's a great variety. I feel like I just went out on an international excursion. We're so happy to have all of you here with us today. That's terrific. Great involvement. What an international world we have. Okay, we're going to run some experiments now. Maybe that gave you a chance to look at those schematics for our test apparatus here today. And the first thing we're going to do, if you've got one of those diagrams open, is we're going to take the pump and we're going to flow into the A port on the base, and we're going to have oil coming out the B port on the annulus, and we're going to start with that 2-to-1 cartridge where there's twice as much surface area on the base as there is on the annulus. Are you following that? So as far as the surface areas at the bottom of the cartridge are concerned, 2/3 of the surface area is on the A port and 1/3 is around the annulus. 3/3 is always available, right? Up at the top on the pilot port. So if you look at that 2-to-1, or where it says 50% of the top is equivalent on the annulus, probably the simplest way to make it even simpler is to say that it's a 2/3, 1/3. 2/3 surface area on the base, 1/3 around the annulus at the B port. And we're going to be hitting that A port. Look at the pump down there at the bottom of the schematic. We're going to be hitting the A port. It says down there, we're going to hit the A port with 1,000 PSI pressure compensation set on our pump. And our maximum volume on that pump has been pre-adjusted to 1 gallon per minute. So that's our flow rate.
Maybe mention too that we're going to be using that schematic 4 different ways, so we're going to have to be a little flexible.
Thank you, Mark. Yeah, Mark just mentioned to remind you that you're going to have to be a little bit flexible what you view here. So we're going to use this schematic about 4 different ways, because we're also going to take the A and we're going to pump it in. Sorry, we're also going to take the pump later on and pump it in on the B port annulus and reverse things around. So let's get ready to go here. We've got our pump all pre-configured. Oh, I should tell you about these 2 pressure gauges. These 2 pressure gauges are about to become fairly important. And we've got 1 pressure gauge on the right, which is always going to be watching our pump outlet pressure. So that's not going to change no matter what we rearrange in terms of hoses and connection. The digital gauge on the right is going to watch our pump outlet pressure maximum. So and it's watching that pressure, by the way, right as we enter into the cartridge. So we're going to start with this manifold here. There's the lower port. We mounted it horizontally, and the cartridge is loaded in under the cover here. And there's our pump coming in, and here's the microbore hose that's running up to the gauge on the right. So we're measuring pressure for the flow coming in. And then here is the port that is higher up, further out, because we're horizontally mounted. That's the B port annulus, oil coming out, and that oil is going to this flow meter. So we're going to want to keep our eye on this red line and see when it lifts off the bottom, and then we'll know that flow is passing through the cartridge, so the cartridge is open. Pilot pressure is being brought in externally. You could see that on the schematic if you opened it at your location. And that pilot pressure will be introduced by a pressure reducing valve that we will reduce down from the top pressure of 1,000, and we'll be watching that pilot pressure on the left. That'll always be pilot pressure on the left digital gauge. Okay, so that's basically the scenario that we're running with. This is the Rexroth 2-to-1 cartridge, as they like to call it, but probably the simpler way to speak of it is 2/3 of the surface area is on the bottom A port and 1/3 is on the annulus B port as far as surface areas at the base. 2/3, 1/3. I hope that makes sense to you. All right, I'm going to turn on the pump here and we'll get going. So our pump is on. As you can see, we're pretty close to 1,000 PSI. I said that was the pressure that we adjusted our pump's cutoff. There it is. We've arrived. There's no flow going through the cartridge. The red line of our flow meter is sitting on the bottom. It hasn't even moved a little bit. Now, we're pushing 1,000 PSI against the 2/3 surface on the bottom, and we have the 3/3 surface available to us, if you will, on the pilot port. So what would you guess? I'm going to start turning down the pilot pressure to the 3/3 surface, that pilot surface on top. I'm going to start turning that pressure down. What pressure do you think I'm going to need to come down to before we see some flow occurring, before this valve is going to crack open? 3/3 surface area available on the top, the pilot port. 2/3 surface is available equivalent on the base port, the A port. And so I'm thinking some of you have already calculated that based on the 3/3, 2/3 numbers I've been throwing at you. And so I'll come down into the 600s because I bet you guessed a number in the lower half of the 600s by now. And so here we come. We're coming down to 650, 655, and keep an eye on our flow meter to see the moment at which it moves. We're at 640 psi. I'll call them out. There it is, 640 psi, 635, somewhere in there. That's 2/3 of our maximum pressure is what our pilot pressure is, just starting to duck below that 2/3. And sure enough, our valve has cracked open and flow is passing, base flow, A to B. Okay, that's how that works. Pretty straightforward. And of course, as I continue to reduce pilot pressure, the poppet will open further and further. Okay, for now I'm going to limit it to that. We have a very small amount of flow in large cartridges, so there's not much need for me to crack that wide open. But as I come back up to 640 or higher, I'll even go higher, I'll go up into the 800s. You might say, okay, well that flow is blinded out and that cartridge is blocked off. Well, remember, we're introducing pilot pressure, from an external source, and we're pushing our pump's flow from the A to the B port, and it's always possible that there may be some leakage then down along the sleeve, between the poppet and the sleeve. And so let's find out whether or not we're truly check valve closed. We're going to open up that secondary needle valve that you see in your schematic, and that needle valve just opens up the B port side to see if we really are cut off, because the flow meter only has so much resolution. It may be sitting on 0, but maybe it just isn't accurate enough to show us that there is a small rate of flow. So what we did is we connected a small microbore tube that you see in the schematic from the B port side to a little port on our tank, and there's a little bit of a tubing inside bent at 90, and if you see those drops splashing on top of the oil there, one every couple of seconds, I'd say about one every 5 seconds or so, what you can see is that the cartridge is not locked completely tight. That is the disadvantage in working with that particular arrangement, whereas if we put the bleed needle valve on the opposite side, when treating it as a check valve B to A, annulus flow, we wouldn't see that leakage. So
That's why we did that, so we don't open bucket test.
right, as Mark wanted to point out, the reason that we put that microbore hose and the needle valve into the tank is that detecting small flow rates is difficult. There's not a lot of flow meters that work with those minor drops per minute that can give you a flow rate. It's just not done. And so a lot of people end up just putting drops into an open bucket, and there can be certainly some hazards that go with having a test hose open to atmosphere if scenarios were to change in a hurry and you didn't control it. You could put yourself at risk safety-wise. So in our case, we're dripping into the tank, and our experiment is controlled from a safety point of view. Yeah, thanks, Mark, for reminding me of that. That's great. Okay, we're going to switch over now. And now what we're going to do is we're going to switch over the apparatus and change to, Mark opened a bleed down valve there so that we take all the pressure out of our system before we change our plumbing. Yeah, maybe I'll hold one for you. So now we're going to put our pump on the annulus port. Pump on the annulus port, same cartridge. We still have the 2-to-1, but now we're coming in with the pump on the 1/3 annulus side, and we're going out to the flow meter and back to tank on the 2/3 base side. So we've just reversed the plumbing at the cartridge, nothing else. And we're going to fire up once again here. I'm just going to get my pressure reducing valve ready, which introduces our pilot pressures. So remember now, pump is coming in on the 1/3 annulus surface, where 2/3 are available on the base. And remember, 3/3 are on the top of that cartridge, the pilot port. So based on surface areas, I think you already know what pilot pressure I'm going to need to come down to before that same 1,000 psi coming from our pressure compensated pump acting on a smaller surface area, that ring annulus, being able to push that valve open and see some flow on our flow meter. So let's head on down. What number are you guys guessing at? Who wins the prize today? Let's see what we should send somebody, I guess, some pocket booklets or a mouse pad probably. All right, we're coming down here. Let's see what number we get. Are you guessing something down there in the 300s? So we're down at 400 psi. I'm reducing the pilot pressure. Remember, the right-hand gauge is just watching the pump's maximum cutoff pressure, pushing on the B port this time. And we haven't seen our red line lift off yet, but I'm coming down very slow. I want to try and get this number as accurately as we can. So we're at 347 psi on the pilot pressure from the top of the cartridge. We're at 337. 332. Oh, there we go. Did you see the line lift off? You saw a little bit of flow? I'm just trying to find the sweet spot there by moving my pilot pressure. Well, it's somewhere right around 325, 330. So if you guessed 1/3 of 1,000 psi, you were correct. It's pretty close to being exactly 1/3, and that's 1/3 the surface area of the entire available poppet. Well, that's it. So we now understand a little bit more about that particular differential cartridge, and I think that proves the functioning of that. All right, we'll shut off and depressurize, and we're going to rearrange. Hey, Joel guessed correctly. Thanks for your guess there. Thanks for your guess, Joel. And you had exactly the right number there, so thanks for being willing to venture that online. Not everybody always wants to ask that. So send us your email address, Joel, and we'll send you something fun from lunchboxsessions.com. If you feel that you don't mind letting us know how to get in touch with you, you can email us at info@lunchboxsessions.com, Joel. All right, Sammy had asked a question. Let's see what he says. Cartridge valves are used as directional valves, pressure valves, flow valves. Yeah, lots of things. So if we use it in one circuit as directional, for example, must we use other cartridges for flow and pressure? Oh, I see. You're asking, can one cartridge in one position, maybe in the manifold, do more than one thing at a time? I think there are some examples out there where you see a little bit of combination. Certainly directional and flow come packaged together. And I'd have to scratch my head now, Sammy, to think about whether we've seen other combinations. Yeah, I think all the pressure applications that we see are pretty much just for that. Yeah, I'm not sure off the top of my head. That's a really good question. Flow and directional can be packaged together, and maybe that's the only combination example I can think of at this exact moment. Great question, though. Mubaris had asked a question earlier about troubleshooting resources. Hey, Mubaris, we'd recommend lunchboxsessions.com. We've got some great troubleshooting lessons in the hydraulics menu, so feel free to subscribe and join and let us know. We'd like to think of our website as a bit of a digital textbook, so feel free to try that out and give us your input.
Troubleshooting these, you have to kind of consider, you must understand how they work before you can determine what could be going wrong. So that leads to learning more about them, and you get that by practice and playing and reading and studying, just like somebody asked earlier, just time.
I had to share my microphone with Mark, so did you pick up on that? Mark and I have often said, so much about troubleshooting starts to become more clear as you learn the normal functioning. We often say half the battle in troubleshooting is knowing all of your normals, how things work, how they're meant to be adjusted, what their normal performance parameters are like, and once all those things are locked in, the troubleshooting aspect gets so much simpler. All right, I think while I was chatting with you and answering questions, I think Mark rearranged the circuitry, and so thank you, Mark. Mark has now moved our pump over to feed the A port, the base port, on the 14.3:1 cartridge. This is a cartridge that has a very skinny annulus on the B port. Okay, but so far it's going to be really easy. We're just going to come in the A base port and flow out the B port. We've got our throttling control rod, the travel limiting rod, we've got that backed all the way out. So that's not going to interfere. But we do have a cartridge in here with a damping nose on it, so that if we wanted to do experiments with flow and what have you, we could dial that in, and the control rod would go down and get closer to the bottom. It's inside the middle of the spring, and we get close to the bottom of the poppet and limit its travel. But I'm going to leave that one backed out. And then, as usual, Mark hooked up our pilot port is external. Pilot pressure is external. And so we're working on a much, much larger surface area. And so if we're working on a surface area from the top that is only slightly larger, it's only slightly larger surface area from the pilot port on top as opposed to the A port, base port on the bottom. And we start off with that same 1,000 PSI. Start off with the same 1,000 PSI from our pump. So our pump is on. And we're closed in there. Okay, so we are all set to go. We'll just let the pressure come up on that right-hand digital gauge there to let us know that everything is kind of nominal. Okay, so we got 1,000 PSI from our pump pushing on the right-hand gauge there. That's the A port, the base port. And I should dial up my pilot pressure as high as I can get it there. All right, so I'm going to start backing down the pilot pressure, and remember that the remember that the pilot port, area X, at the top of the poppet, which is the largest surface area, is only slightly larger this time than the base port. This is that 14.3 to 1, where you've got what would be considered 100% on the base, 7% on the annulus, and 107% on the pilot area up at the top. So let's see, who's going to guess the correct pressure? Go ahead and fire us the numbers if you like. Let's see who can get us the closest to the pressure that, just for fun, we're going to watch the red line on our flow meter, and go ahead and throw us your calculation, or best guess if you don't feel like calculating. And let's see, so we're down to 975 PSI. 965, 948. Oh, I better slow down. I got a little carried away there. 920, 918, 916, 915. Red line hasn't moved yet. 911, 910, 903. Red line hasn't moved. 889, 875. Oh, I think it lifted there. There we go. So we were at about 860, 865 when that red line came off the surface. Yeah, if I go any further, down to 840, we can see the red line really lifting up. So somewhere around 865. Let's see if I can find the sweet spot here. Yep, somewhere right around 865 PSI was the point at which the pilot pressure on the top area X was no longer sufficient to stay closed against that almost as large base port surface area. All right, so we've proven that one out. I'll turn back up to the highest pressure here, and we'll shut down, and we'll just do one last test and see, can you indeed get flow to pass from the B port to the A port, and what kind of crazy pilot pressure might it take to reduce down to let that poppet come off its seat. Okay. All right, Mubarak was the closest on that one at 900, and that should have been the number. I think yesterday, it was around 890 or so by calculations, 900, somewhere right in there. And why it's a little different today, different temperatures, I'm not entirely sure. It's Tuesday, Mark said that's probably the reason. Yeah, there you go. So yeah, Mubarak, send us your email if you like to info@lunchboxsessions.com, and we'll send something interesting to you. All right. Joel was asking, you must have a schematic to troubleshoot. Yes, thank you, Joel, for mentioning that. Yeah. Oh, those manifolds with all those cartridges in there. Yeah, I mean, like Mark was pretty concerned too when we started to just put together our apparatus that we better provide some kind of a schematic. And yeah, you're right. When you look at the schematic for the control hydraulics on a large plywood press or an oriented strand board press, it is a dizzying array of things. I can't imagine how anyone would begin to do effective troubleshooting without being able to discern the different subcircuits and potential flow paths and what have you. So true. Very good point. Thank you. We've had additional visitors joining us from Jordan and Peru and Turkey. So thanks for logging in to interact with us today. That's much appreciated. All right, I think Mark has changed the apparatus around. Thanks for doing that. So now we're pushing with the pump on the really skinny annulus part, the 7%, where the 100 is on the bottom, 107 is on the top. So, okay, one more shot at firing off to us your best figuring about what pressure I'm going to drop the pilot pressure down to on the control cover before we might pass some flow. Okay, go for it. Give us your numbers while I'm dialing down. What do you think? Do you think I have to dial down pretty far? Let's see what happens. Because remember, 1,000 psi on the B port is now pushing on a pretty skinny annulus, whereas the advantage we have from the top is a very large surface area, so we won't need much pressure up there to create an equivalent force. Right? It's about force equivalence, bottom versus top. If we're going to talk raw units, it's a force units versus force units competition, top versus bottom of the poppet. So we're working on that skinny annulus with the 1,000 psi from the pressure compensated pump. And I'm just going to dial down a little bit more aggressively here. And maybe let's have a look at those two gauges there. And let's see, my pilot pressure is already down at 200. And I can tell you we're not there yet. That red line on our flow meter isn't going to move just yet. I got to keep going. Big surface area at the top compared to the 7% skinny annulus. And this system may not be that stable once it gets open. This is not the typical poppet to use for continuous flows back B to A. All right, we're down at 80. We're down at 85. We're down, and maybe I should have hit the digital menus on those gauges today, since our audience is so international. We should have done all of it in bar or kPa, I suppose, right? But there you go. They're just units, and we're all capable of transposing the meaning of the units as a generic value, so that's what we'll call it. So we're down at 60 psi. Pressure on the top just shows you the power of surface area, right? We've got the whole surface area of the diameter of the poppet at the top where piloting takes place. I'm not sure I can even dial that low. I think I might be out of luck. I'm at the bottom. Yesterday we managed to get a little bit lower, around 50 psi. Now it doesn't look like I can even get low enough to get this one to open. So 60 psi times the square surface area on the top of the poppet was enough to keep us closed against a more or less. So probably not the poppet you're going to choose if you are actually going to return flows back. If you're going to flow annulus B port to A port. Okay, we didn't manage to get open. Interesting enough, right? We'll shut down our pump. Right, yeah, we do have. Mark is pointing out that, of course, as we come out of our B port, let's see, we're coming out of our A port in this case, and we're flowing through a flow meter and then through various couplings. So we do have resistance on that downstream line as well. So whatever the causes are, we don't have enough pressure differential to unseat that cartridge, and it isn't a normal cartridge to use for having B to A flows. All right. So Naveen Sang, thank you for your guess. Your calculation was probably correct, and I wasn't even able to get my pressure reducing valve to go down that low. Feel free to send us your email address, to info@lunchboxsessions.com, and we'll find some way to get something to you for your willingness to take a guess at that. Thanks, Naveen. All right, a question from Danilo Martins, the difference between the 330 and the real value. Oh, yes, thank you. I forgot about that. You're right. Easy to forget about that spring, right? That spring on top gives you a little bit of a bias force in addition to the pressure force from the top. And it's so easy for me to forget about that when I'm just thinking about the various ports and passages that spring is still there and contributing. And I'm just going to reach over Mark while he's doing that, and we'll just check and see what spring we had in on that one. Oh, guess what? The spring on that one, on that last one we were doing, was only a half a bar spring. Oh yeah, but Danilo, you're referring to the first one we worked on, so I know what you're referring to. So on that first cartridge we worked on at 2-to-1, let's see here. It says on the outside that we've got an A10, E7. Yeah, so that 10, we got a 1 bar spring in there. So that's adding about 15, around the 15 PSI mark. But you're right, that is a factor, and sometimes the springs are as large as 4 bars. Could be up to 60 PSI and thereabouts. So there's a second schematic in the CDIG Logic Cartridges PDF that we put there on the site. Logic Cartridge C at the bottom of our test panel here. And you'll want to dig that one out. And notice that there's a solenoid operated valve mounted on top of this last cartridge. You'll notice that we're taking the pilot pressure, not externally this time. This time we're going to grab that pilot pressure off the A port through a 0.15-inch diameter orifice. That's pretty small. We showed you that one back at the beginning. And that's going to travel through the directional valve when it's not energized, and push down on the top of the pilot surface area and keep that pilot valve closed. And then when we turn the solenoid on, you'll see that the pilot area at the top of the cartridge will be connected to the downstream side, to the B side, through another 0.15 orifices. And the B side is largely on its way back to tank. A flow meter, as you can see there, F2, and some quick couplers and some hoses. Mark's got some input.
I just put there's a quick coupler, not on the schematic, but that's where we got our pilot gauge pressure. It's coming in there.
Okay, yeah, he's just pointing out that the one connection that we do have off the right-hand side there is just measuring the pilot pressure that is present on the top of the poppet. All right, so I think we're all set to go. We've got power over there. So here we go. We're going to fire up and see what happens. Yeah, you're good? Okay. All right, we rearranged a lot of things, so there's a little air shock somewhere in the system. Okay, so what you can see now on the right-hand gauge is that we've got 1,000 PSI from the pump pushing on port A. Now you can really see on this manifold that port A is the lower of the 2 ports on that cavity. Port B is higher up on the annulus coming out. We've got the 14.3-to-1 down in there because we only flow the oil in one direction here. And right now there is no flow. And we can see that on the flow meter, that there is indeed no flow. And I'm going to go over and energize the solenoid on this valve with a switch that's way far away. And when we energize that solenoid, we take that pilot pressure on top of that poppet and we connect it to the B side, which is for the most part on its way back to tank. Oh yeah, there's our flow, right? And while that poppet in that bottom cavity doesn't have a damping nose on it, there are the 0.15 orifices, and so you will see some little bits of delay here. As I turn the solenoid off, you know, you could say it's somewhat dampened a little bit just by the 0.15 orifice in use. Not really proportioning or anything like that. As I turn the solenoid back on, yeah, you know, still some degree of an on-off scenario for sure. If you wanted something softer than that, you would have to tackle it with other types of control valving on the top, like a proportional, or move to the type of throttling valve that we'll demonstrate here before we're done. Was there anything else, Mark, that we were going to do with this particular experiment? Okay, I think that was it. Okay, good. So then let's just close off. Yeah, we're off on that one. I think we need to go off there. What else do we need to do? I think we need to go on here.
Open that.
There we go. Anything else we need to do? I think that's it.
Stuff out of the way.
Yeah, go ahead and turn the pump on then for us, if you will, and we'll see if the camera can come on over to here. So just as our last little demonstration, we have that two-way proportional throttling valve with a very direct connection of the solenoid and controlling devices inside to the Poppet for both push and for pull. The camera's making its way over here, so we'll just give a second for that. This is that FES 25, a document that you will see loaded in there on the list of documents for today's live broadcast. If you're looking at the symbol down here, there is that alternate symbol that has been popular in the DIN symbol set in the past. And this is not just a proportional solenoid with variable current going into it, but also a second cable. What's that second cable for, everybody? Who's going to call that one out? Let's have one more pop question for today's final quiz for the group. We'll send somebody a mouse pad or a symbol booklet or something nice, and feel free to let us know what that second connection is. This one's the drive. This one's the drive solenoid variable current. What's this other cable coming off the back here with a skinnier looking apparatus? Feel free to take a shot at that one. And so let's see if I'm ready to go here. Run my motor. Probably missing something. Oh, I know what it is. My pressure bleed circuit is open. Got to close that in. Okay, that's good. That was a safety circuit that we opened when we were changing our plumbing around. So yeah, now we're in a scenario where variable current can be sent to a proportional valve solenoid, the one in front here with the larger connector, and very physical connection to the Poppet itself. It's not a floating Poppet, physical connection to the Poppet, and so very, very fine controlling of flow can be done. And even though this valve size is easily good for 80 gallons a minute, 300 and I can't remember what it was, 350, 360 liter per minute rating, with the tuning done to the gain on the amplifier card, a little gallon and a half per minute or 1 gallon per minute flow that we've configured our pump for today is able to give us no end of variability. And so this type of valve loads into the very same cavities. You know, someone was asking before, what are the advantages of thread in versus slip in? Well, there's a lot of similarities, of course, but there's an awful lot of versatility for what comes and goes from those various NG cavities. You can see our pump outlet flow over there on the hydraulic power unit where there's a turbine flow meter letting us know that our variable displacement piston pump, that's an oil gear PVWJ that's in use on that one. We really like that model of pump. A lot of robust control features. And we'll be wide open here at 1 gallon per minute. We're pretty close to it. We're producing 480 some odd RPMs on our hydraulic motor. And so lots of controllability with that type of device. Not exactly the same isolated slip-in cartridges that we started with, but from the same groupings of technology that work into that slip-in cavity. All right. Hey, apparently Joel was the first to answer on that one. We'll find out what his answer was here in a second. Andrew, though, for the meantime, is saying, I'm looking at a bent axis piston motor, a Rexroth, and it says it has variable displacement. You have to let us know what model that is. There are some that appear as though they are bent axis, but still have controllability on the inside. That is true, but you'd have to let us know what material that, what model number you've got there, and we'll help you try and find some material for that. Yeah, Joel's first answer was it was feedback. You're right. LVDT was what that other cable was that's hooked up. Linear variable differential transformer. That's a mouthful, LVDT. And yes, that's feedback. You're absolutely correct. And Katharina answered position sensing, so that's also correct. Excellent, both of you. So both of you, feel free to send us your email address or however you'd like us to communicate with you. Send that to info@lunchboxsessions.com. That'd be great. I think that's about all we have time for today. We've gone on long enough. Hopefully we've answered everybody's questions. And so thanks again so much for being with us for our fun exploration of hydraulics. And thanks to Mark for giving me a hand today. Owen's been on the camera, and in addition to Carl, Owen, and Mark, CD Industrial Group, and those who make up lunchboxsessions.com also include Nathan, Crystal, Robin, Chris, Ivan, Alex, and Lenore, and special mention also to Ted, Keelan, Emily, and Grant for their contributions throughout this past year. Wonderful to have such a great team. And thank you to our partner in our broadcast series this year, Fluid Power World. So remember fluidpowerworld.com for the technology conference going online this year. Our next live broadcast will be way down on August 25th, so we'll see you then, where we'll be doing some more fun things with load sense, hydraulic systems. Thanks for joining us, everybody. This is Carl from lunchboxsessions.com, and we'll see you next time. Bye-bye.